Hello and welcome to the CompTIA Cybersecurity Analyst CySA Plus Certification Study Guide. In this video, we will discuss Chapter 5.4, More Tools for IOC Analysis. Please like, subscribe, and leave a comment. Although packet analysis is important, examining raw data packets is considered too slow to identify IOC. Flow analysis, also called network traffic analysis, is the evaluation of a collection of network data. Instead of examining the individual performance of a device on the network by looking at raw data packets, network traffic analysis is an aggregate or collection of data from the network's different devices. One of the primary reasons why network traffic analysis is used in this way is because, as the network itself becomes the connective link between local resources, virtual computing, and remote cloud servers, it has become the optimum means to view the security of the information technology infrastructure as a whole. Flow analysis has been performed for many years in order to troubleshoot network issues and identify performance bottlenecks by identifying which applications are hogging resources and bandwidth. The analysis usually looks at overall network utilization and speed by generating statistics based on the flow of data through the network. However, flow analysis for cybersecurity is different than traditional network traffic flow for several reasons. Eliminates monitoring agents. Threat actors often attempt to disable separate software monitoring agents that are installed on each network device, and some systems, such as database servers, application servers, DNS and DHCP servers, Internet of Things devices, and embedded systems, cannot accept monitoring agents. However, by using network traffic analysis, network data can be collected passively and quietly so that threat actors cannot interfere with the data collection. Eliminates monitoring agents. Threat actors often attempt to disable separate software monitoring agents that are installed on each network device. And some systems, such as database servers, application servers, DNS and DHCP servers, Internet of Things devices, and embedded systems, cannot accept monitoring agents. However, by using network traffic analysis, network data can be collected passively and quietly so that threat actors cannot interfere with the data collection. Uses deep packet inspection. Unlike traditional network traffic analysis that only looks at the flow of data through the network, network traffic analysis for cybersecurity extracts metadata, data about data, from the network packets and then converts it into a readable format using what is called deep packet inspection. This can even facilitate decryption of application traffic and its contents so as to identify suspicious activities. Provides richer information. In addition to standard network analysis, such as identifying bottlenecks, deep packet inspection can identify what devices are active on the network, what applications and protocols they are using, and what data they are accessing. Also, alerts can be set to advise security administrators of any unusual activity or network anomalies. Flow analysis is often used in identifying a ransomware attack. Flow analysis can detect when multiple file names are being changed, which is a typical indicator of a ransomware attack, and an alert can be generated in real time. The output from a flow analysis network traffic analyst tool is shown in Figure 5.13. Flow analysis data can be accumulated from different sources. NetFlow is a session sampling protocol feature on Cisco routers that collects IP network traffic as it enters or exits an interface and uses TCP/IP Internet Control Message Protocol, ICMP. Echo request packets. SFlow is a packet sampling protocol that gives a statistical sampling instead of the actual flow of packets. IPFix, IP flow information export, is similar to NetFlow but adds additional capabilities, such as integrating simple network management protocol, SNMP, information directly into the IPFix information so that all the information is available instead of the need to query the SNMP server separately. In 1989, Tim Berners-Lee, a British scientist, created the World Wide Web while working at CERN, the European Organization for Nuclear Research. The first website was fittingly CERN, info.cern.ch. By 1992, the web had grown to 10 websites, but 2 years later there were 3,000 websites. In 1996, Google was launched and started scanning the 2 million websites that were then in existence. As of mid-2023, there were over 1 billion websites on the internet, with 250,000 new sites added daily. The most visited website in the world is Google, followed by YouTube, Facebook, X, Twitter, and Wikipedia. However, just as new websites are added to the internet every hour, so too has the proliferation of malicious websites increased. It is estimated there are over 67 million malicious domains and URLs. Is it possible to identify the reputation of website as to it being legitimate or malicious, to which a device has connected by examining its IP information or DNS information in order to uncover an IOC? This is known as DNS and IP reputation. One reputation tool is WHOIS, which is a TCP/IP query response protocol for accessing information about internet resources, most notably domain names and IP addresses, as well as internal contact information for websites. It was originally designed to identify those individuals who are responsible for the different network resources, but today is used to obtain domain name information. However, much of that information can now be hidden, redacted, for privacy purposes. A WHOIS lookup for www.cengage.com in Figure 5.14 shows a typical response with limited information for determining the reputation of a website. Another reputation tool is Abuse IPDB. This website serves as a central repository to identify IP addresses that have been reported as being associated with malicious activity online. Abuse IPDB serves as a deny list that can be downloaded and used to block access to malicious sites. In addition, malicious sites can also be reported to Abuse IPDB to be added to the deny list. The Abuse IPDB website is seen in Figure 5.15. The Abuse IPDB website receives over 22 million submissions each month. Log correlation and analysis tools. Logs play a critical role in identifying IOC. There are issues surrounding log management, and it is important that logs be consolidated for analysis. Log management issues. A log is a record of events that occur. Cybersecurity logs are particularly important for an IOC because they can reveal the type of attack that was directed at the network and how it successfully circumvented existing security defenses. Firewall logs. Firewall logs can be used to determine whether new IP addresses are attempting to probe the network and if stronger firewall rules are necessary to block them. Outgoing connections, incoming connections, denied traffic, and permitted traffic should all be recorded. Intrusion Detection System, IDS, Intrusion Prevention System, IPS, logs. Intrusion detection and intrusion prevention systems record detailed security log information on suspicious behavior, as well as any attacks that are detected. In addition, these logs also record any actions IPS used to stop the attacks. Application logs. Application log files can give information about attacks focused on different applications. If an application log identifies an app that has been the source of a compromise, software can be used to create a dump file, which is a snapshot of the process that was executing and any modules that were loaded for an app at a specific point in time. Endpoint logs. Endpoint logs can provide a wide range of reports and alerts with events classified by their severity level, such as system events, software installations, removable disk activity, Windows registry changes, and login and session activity. OS-specific security logs. OS logs typically record system events that are operational actions performed by OS components, such as shutting down the system or starting a service, and audit records that contain security event information such as successful and failed authentication attempts, file accesses, security policy changes, account creation and deletion, and use of privileges. Network logs. Network logs can come from different appliances, such as router and switch logs that provide general information about network traffic. Metadata logs. Metadata is data about data, or data that describes information about other data. However, the logs listed in Table 5 are categories of logs and not a listing of the individual logs that are produced. Within each category, there are multiple types of devices that produce these logs: firewalls, IDSs, IPSs, web application firewalls, WAFs, network address translation gateways, next-generation firewalls, unified threat management, UTM devices, proxy servers, and so on. And each type of device may have multiple devices producing logs. That is, multiple firewalls each produce their own individual logs. Finally, the volume of detail in each log produced is granular. Consider a single basic firewall log that displays the connections that are permitted or denied through the firewall. Typically, a basic firewall log would contain the selected fields listed in Table 5, 6. However, there is no standard. Vendors include their own choices of information. It quickly becomes apparent that there is a massive amount of log data generated related to cybersecurity, and the amount of data is not the only issue surrounding log management, which is defined as transmitting, collecting, analyzing, and disposing of log data. Other log management issues include all events recorded. Devices record all events, even those that are not cybersecurity related, which increases the amount of data that is generated. Conflicting interpretations. Each type of device may interpret an event in a different context, so that a router looks at an event differently than a firewall does. And this can produce different alerts. One device may see an event as only a warning, while another device may interpret it as a serious event. This can create a confusing mix of log data, different log formats. Different devices record log information in different formats and even with different data captured. Manually combining multiple logs, each with a different format, can be a major challenge. One solution to the problem surrounding cybersecurity log management is log ingestion, which is the process of formatting and uploading log data from the different sources that generate log data to a central location for analysis. Log ingestion also transforms unstructured log data into a structured format so that it can be queried and filtered more easily. Log ingestion involves synchronizing timestamps of the different logs and identifying the various logging levels. Because log ingestion involves combining log data from a variety of sources, it is critical that the recorded times of a single event all match. Time synchronization. Otherwise, it would not be possible to see the impact of a single event on multiple devices, or erroneously think, because the times do not align, that the same event was actually two separate events. Typically, network administrators implement the Network Time Protocol, NTP, to synchronize timekeeping across a set of distributed time servers and clients. NTP runs over the User Datagram Protocol, UDP, using port 123. The NTP network of servers typically obtains its time from highly accurate atomic clocks or GPS clocks linked to time servers, and NTP is used to distribute this time across internal networks. A logging level is a means of classifying log entries in terms of urgency. Classifying helps filter log files by controlling the amount of data in a log. Table 5, 7 lists the different logging levels from most data accumulated to least data accumulated. An example of the different logging levels can be illustrated by a user logging into a system. Successfully logging in is normal and logs an info event. However, a user who enters the wrong password is rejected and logs a warn event. After 3 unsuccessful attempts, the user is locked out of their account, and this generates an error event. Despite the value of log ingestion, it does not solve log management issues. There is a need for highly automated log analysis tools. Some of the primary tools are security information and event management, security orchestration, automation and response, and endpoint detection and response. Security information and event management, CM. A security information and event management, CM product, usually pronounced SIEM instead of SIM, consolidates real-time monitoring and management of security information with analysis and reporting of security events. A CM product can be a separate device, software that runs on a computer, or even a service provided by a third party. A CM dashboard is shown in Figure 5:16. A CM typically has the following features. Aggregation. CM aggregation combines data from multiple data sources, such as network security devices, servers, and software applications, to build a comprehensive picture of attacks. Correlation. The CM correlation feature searches the data acquired through CM aggregation to look for common characteristics, such as multiple attacks coming from a specific source. Automated alerting and triggers. CM, automated alerting and triggers can inform security personnel of critical issues that need immediate attention. A sample trigger may be alert when a firewall, router, or switch indicates 40 or more drop reject packet events occur from the same IP source address occurring within 60 seconds. Time synchronization. CM time synchronization can help correctly identify an event as one single event and not multiple events that have varying timestamps. Event duplication. When the same event occurs that is detected by multiple devices, each will generate an alert. The CIEM event duplication feature can help filter the multiple alerts into a single alarm. Regulatory compliance. CIEM devices usually provide a built-in template to support and record specific regulatory compliance. CIEM logs can also be retained for future analysis and to show that the enterprise has been in compliance with regulations. Security orchestration, automation, and response, SOAR. An orchestra is a large instrumental ensemble, group, that plays a variety of types of music, composed of 4 families of instruments: strings, brass, woodwinds, and percussion. A full symphony orchestra can have over 100 members, while a smaller chamber orchestra may still have up to 40 different members, depending on the music being played. The conductor is responsible for bringing the orchestra to a specific interpretation of the piece being played while leading rehearsals. The conductor takes apart the piece of music during rehearsals to practice with the different families and groups of instruments before bringing everything together in the performance. A symphony orchestra is seen in Figure 5:17. A symphony orchestra is defined by its string family. Without the strings, it would be classified as a band. In recent years, the concept of a musical orchestra in which many varied instruments all work together, called orchestration, has made its way into cybersecurity. Often called workflow orchestration, it involves the automation and combination of many different individual tasks and processes. In contrast to cybersecurity automation that only automates one task, workflow orchestration involves organizing many tasks into a functional process, workflow, that is automated. In other words, workflow orchestration is automation used for entire processes instead of for a single task. The various components of workflow orchestration are large and complex. This is because they cross multiple platforms and involve hardware, software, middleware, and services, and use multiple automated and sometimes semi-automated tasks to automatically execute a workflow. Although on occasion cybersecurity literature will use cybersecurity automation and workflow orchestration synonymously, this is incorrect. Security automation is setting a single security operations-related task to run on its own without the need for human intervention, whereas workflow orchestration is automating multiple tasks that make up an entire process. Workflow orchestration has given rise to a new type of cybersecurity platform known as a security orchestration, automation, and response (SOAR) platform. SOAR is a combination of software programs and tools that allow organizations to synthesize and automate a range of security operations, threat intelligence, and incident response in a single platform. Figure 5:18 illustrates a SOAR dashboard. In Figure 5:18, the SOAR dashboard displays a dollar saved amount, which is a common feature. The function of a SOAR platform can most clearly be seen when compared to a CIEM product. A CIEM consolidates real-time monitoring and management of security information with analysis and reporting of security events. It can perform automated alerts and triggers to inform security personnel of critical issues that need immediate attention. A SOAR, on the other hand, can go farther and automatically take immediate action against the threat. This means that a SOAR can perform as both an IOC and an IOA. Consider a threat actor who is attempting to use a brute force attack against a login prompt. Normally, this would result in a human security administrator receiving an alert. The administrator would then have to open the firewall app and manually block the IP address of the attacker. However, when using a SOAR platform, the SOAR can automatically and immediately block the IP address of a computer that is attempting to brute force a login. CIEM and SOAR devices are not competitive and alternative technologies, either or, but are complementary tools, both and, that help organizations respond to security threats. Whereas a CIEM helps SOC teams detect threats based on data collected from applications and the infrastructure, a SOAR responds to threats in a more efficient manner. Endpoint detection and response, EDR tools have a similar functionality to host-based intrusion detection systems, HIDs, of monitoring endpoint events and of HIPs of taking immediate action. However, EDR tools are considered more robust than HIDs and HIPs. First, an EDR can aggregate data from multiple endpoint computers to a centralized database, so that security professionals can perform further IOC investigation and also gain a better picture of events that are occurring across multiple endpoints instead of just on a single endpoint. This can help determine if an attack is more widespread across the enterprise, and if more comprehensive and higher-level action needs to be taken. Second, EDR tools can perform more sophisticated analytics that identify patterns and detect anomalies. This can help detect unusual or unrecognized activities by performing baseline comparisons of normal behavior. Many EDRs also allow for a manual or user analysis of the data. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. We will see you on the next one.